Ladies and gentlemen, dear colleagues, guests, friends, it's my great pleasure to welcome you all the public section of the section of Engineering Sciences at the Hungarian Academy of Sciences. I also greet the leaders of the Academy, and I especially greet Dr. Qing Luo, First Secretary for the Science and Technology at the Embassy of the People's Republic China in Hungary. As is well known from the invitation card of our session, there is only one item in the agenda today. Based on the proposal of the section of Engineering Sciences, on the 6th of May 2022, the 184th General Assembly of the Hungarian Academy of Sciences elected Professor Haiyan to become an honorary member of our Academy. His inauguration lecture is to be presented today. So there will be a scientific lecture here, which is in the meantime a ceremonial event where the honorary membership of Professor Hu becomes official. This way, as we often say, we celebrate science in general and engineering sciences in particular. Colleagues, friends, and even students who are present, who witness the scientific career of Professor Hu, who collaborate with him in different activities, are also part of this celebration. But it is a special day for the new honorary member too, since he not just makes his membership official, but also has an extraordinary and unique opportunity to introduce this audience to the research area, to the fields where he achieved his professional successes. Before the lecture, let me briefly praise his achievements. Haiyan was born in Shanghai in 1956. He belongs to that specially honored 77 generation which started the studies in a reborn higher education in China. Many students applied for admission to the universities in that year, and only the most talented ones managed to get accepted in the fierce competition. He received BSc and MSc degrees at Shandong University in mathematics and mechanics, respectively, while he obtained the PhD degree for his research results in the field of solid mechanics in the doctoral school of Nanjing University of Aeronautics and Astronautics. As a researcher, he started working in the same institute. Due to his excellent international publications, he was soon promoted. Starting in 1992, with the support of the prestigious Humboldt Scholarship, he worked as a researcher at the Department of Mechanics of the University of Stuttgart for 2 years, which has been and still is a leading center for multibody system dynamics research. After returning to Nanjing, he was promoted and became professor of applied mechanics. In 1996, he spent another year abroad as a visiting professor at the Department of Mechanical Engineering and Material Science of Duke University. He gave lectures regularly at international conferences. His name was already known both in Europe and in North America. Back in Nanjing from 2001, he served as the president of the university for 6 years. Then he moved to Beijing Institute of Technology, where he became a professor of applied mechanics at the School of Aerospace Engineering. He was appointed to be the president of the institute for 10 years. Many from his former 66 PhD students who got their degrees under his supervision work and take part in the Chinese space program, while many of them are back in their home countries from Japan and to India, making successful academic careers there. In 2007, he became a member of the Chinese Academy of Sciences, where he is a member of the Presidium since 2016. He also served as the president of the Chinese Society of Theoretical and Applied Mechanics. During his research work, he established an internationally known academic school specialized in the theoretical and experimental dynamic analysis of nonlinear mechanical structures. He developed the vibration suppression methods to eliminate the harmful vibrations of elastic structures by means of active control in the presence of relevant time delays. These results were then applied for the suppression of the self-excited vibrations of aircraft wings, also for the nonlinear vibration isolation of the jet engines, for the reduction of transient vibrations in large and highly elastic space structures. He wrote 6 books, the most cited of which is the one from 2002 titled Dynamics of Controlled Mechanical Systems with Delayed Feedback. The Web of Science keeps a record of more than 4,000 independent citations for his 210 papers, while he has an additional 150 publications in Chinese, with about 7,500 citations in Baidu Scholar. As an academic professor, Haiyan Hu maintains the scientific heritage of Theodor von Karman in China. His PhD supervisor was also the student of Ludwig Prantl, S. Karman. As we say in Hungarian, Karman Todor. The father of the Chinese space program, Xu Qian, was the most talented doctoral student of Karman in Pasadena. Professor Hu not just knows about this, but he also speaks about it in his lectures, propagates the essential influence of Karman's wisdom on China's space exploration. And now I kindly ask Professor Haiyan Hu to deliver his lecture entitled Deployable Structures in China's Space Missions. Professor Hu, the stage is yours.
Well, thank you so much again, Mr. Chairman, ladies and gentlemen. It's very exciting for me to be here with you, and this is the second time for me to come to visit Budapest. And also the first international visit of me just after the COVID-19. And I'm very honored to be an honorary member of Hungary Academy of Sciences, the most prestigious academy in the world. And today I'm going to talk about the China's space missions together with some of my research related to those missions. First of all, let me say a few words about 2 universities that I've been working with over almost 40 years. The first university I'm going to talk about is Beijing Institute of Technology, that I've been there for almost 16 years. This university was founded in 1940 during the World War II in Yan'an rather than in Beijing. At that time, Yan'an used to be the headquarters of military base against Japanese invasion. The university moved to Beijing in 1949 and then received the current name. This picture shows you the landscape of the BIT campus, and in the middle of the picture you can see the BIT gymnasium used for the volleyball match of Olympic Games in 2008. Very important building. So, the second university I'm going to talk about is Nanjing University of Aeronautics and Astronautics. As Mr. Chairman just mentioned that I spent more years there and received my PhD and worked as a professor and served as a rector of the university. This university was founded in 1952 and focusing on the aerospace engineering. The important issue that the university is located in downtown and at the relics of Ming Palace. As you know, the Ming Palace was built in the 14th century, so more than 700 years ago. The other important issue that one of the founders of the university was Professor Fan Xuji, or called Xuji Fan in English. He received his degrees in California Institute of Technology, also under supervision of well-known Professor Theodor von Karman, the most well-known graduate from the Budapest University of Technologies and Economics. Maybe the former name of the university should be some Józsa University of Polytechnics. I don't know the exact English translation. Anyhow, I can say that NUAA has a part of heritage of Professor von Karman, especially his School of Applied Mechanics. Well, this is a very important figure and relation. Anyway, these two universities are supporting the national defense industries in China, including space technologies and engineering that I'm going to talk about and focus today. Now let me turn to the second part of my lecture, that is China's space engineering. I will talk about the yesterday, today, and maybe something in future in later discussions after the lecture. The first program of China's space engineering was proposed by Professor Xuesen Chen, just like Mr. Chairman just mentioned that. He used to be the best PhD student of Professor von Karman in California Institute of Technology. Then he moved to Massachusetts Institute of Technology, became the full professor. However, he loved Caltech very much and returned to Caltech just after the World War II. Well, by the end of the World War II, Professor von Karman led a military mission to Germany to investigate the research of aeronautics and astronautics of German side. This mission included only 5 people, including von Karman, and Professor Chen was one of the members. This picture is very valuable and shows you that Professor von Karman at the right side, Professor Chen Xuesen in the middle, and the left side is Professor Ludwig Prantl, the supervisor of Professor von Karman. Well, they had the meeting in Göttingen just the end of the World War II. However, after 5 years later, Professor Chen returned to China, proposed the first program to the State Council to develop the long-range rockets and missiles. And this is the very beginning of the China space engineering. So China launched the first missile in 1964. From this point of view, from the standard of today, this is just a middle-range missile because the maximum range is 1,005 kilometers, 500 kilometers. Then China launched the first satellite in 1970 based upon the development of those missiles. I need to emphasize that the total weight of the first China satellite was much heavier than that of Sputnik, launched by former Soviet Union, and Explore 1, launched by the USA. So this represents the capacity and ability of carrier rockets in the old days. Now let me turn to today. As you know, now China has established China Space Station, and this station accommodates 6 astronauts in total. And very recently, last month, the crew number 15 just completed their missions and returned to Beijing. And the crew 16 began to work. And in crew 16, there is a university professor engaged in dynamics and control, my field. By the way, among the 7 astronauts in crew 17, the other astronaut has been engaged in fluid mechanics. So you can see that mechanics is so important in aerospace engineering. Well, in the past few years, China has completed several lunar explorations. The most important thing is the CE4 completed in 2019. It was landed in the far side of the moon, and then the next mission sampled about 1.7 kilo lunar soils and returned to the Earth. These are very important missions in the new century. And in addition, China has completed the first Mars exploration 2 years ago. This mission is very complicated because it is an integration of orbiting, landing, and cruising on the moon surface together. So this also was China's first mission to the moon. So you can imagine that China did not have a lot of information about the Mars surface. We need to detect the surface of the Mars and then decided where is the best location for landing. Okay. Now I'm going to select 2 examples to detail some technologies. Let me talk about the CE4. CE4 means the 4th mission of Chang'e program. Chang'e is the name of beautiful lady in Chinese myths. That's a legend. It's said that this lady swallowed the magic medicine of her husband, and then she flew to the moon automatically. She didn't know how to do it and could not come back. Anyway, she lived in the moon, so China used the name Chang'e to call the lunar exploration. And CE4 is the 4th mission to let the orbiter and the landing platform to go to the far side of the moon. What does far side mean that? Perhaps you know the spinning rotation and the rotation of the moon around the Earth is the same. So we can never see the other side of the moon. So this way you can imagine the difficulty here, how we can communicate and control a satellite and then send the landing platform to the far side of the moon, because it's not possible for us to see it and not possible for us to communicate and control it directly. The other issue, a lot of people ask me, why the landing platform finally choose von Karman's crater. Crater here is a very specific term, means basin due to the impact. So let me talk about the story later. And this picture shows you several locations, CE1, CE4, and CE5, etc. And then the CE4 is in the right picture. This means the far side of the moon. And the blue region in the bottom part means the South Pole region called Antarctic. This is due to the impact of some asteroid. This is a small planet. The astronomy scientist told me that this is the most oldest impact in solar system. Here today, some of people are more familiar with these stories. Anyway, this is a very important location from scientific value, because if we can collect some soils or rocks later on, then we can judge or identify the source of solar system. So anyway, China selected Von Karman crater, and simply due to this is the oldest basin and most flat basin in the far side. Meanwhile, it can offer enough solar sunshine to guarantee our solar power systems and keep proper temperatures for the landing system and rover. And the right picture shows you the exact location of the landing position. The green square in the picture is 15 kilometers wide and 10 kilometers high. So we need to control the landing platform to falling down in this very exact rectangular. This is a very tough problem because we cannot communicate with either the orbiter and platform as well as rovers. So the simple idea to complete the communication and control is to launch a relay satellite to the far side, even far side of the moon, just like the picture shows you that. Actually, we launched a relay satellite to so-called halo orbit around the second launch point along the connection between the moon and the Earth. Actually, more than several hundred years ago, French mathematician Lagrange found 3 points along a line passing through the Earth and the moon. And here is the second Lagrange point. The other point is here and there. And we can use this point because around this point, the centrifugal force of your spacecraft and the summation of all gravitational forces are balanced. So usually we say it's quite clear in those regions. So we sent a communication relay satellite to the orbit. It's about 500,000 kilometers from the Earth and about 740 kilometer millions from the moon. And in humankind history, this is the first time for us to send a relay satellite so far, together with a very large antenna. Because if your size of your antenna is small, then the signal you can receive and transmit it is too weak. That will be useless. So the most important issue for this mission is to design and manufacture a very large antenna in very exact configuration. The final antenna the Chinese engineers designed has 4.2 meters in diameter. In addition, it needs to transmit the X-band signals. This is about 8 to 12 gigahertz. The wavelength is very short. However, the configuration of your antenna reflector must be even smaller than the wavelength. So the basic requirement is that the mean square value should be less than 1 millisecond. 1 millimeter is about 0.83 millimeter. So if you make a simple calculation, you can see that D divided by E is about 5,000. This is very strict requirements for the design of space antenna. Anyway, we did it. The left picture shows you the antenna in the final ground test, and I was involved into a lot of evaluations for this antenna. We need to guarantee that the exact shape we measured on the ground with the impact of gravity cannot influence the real shape when it is centered to the moon's orbit, near the orbit near the moon. So this includes a lot of mechanical problems, mechanics, in particular dynamics. Okay? And the right picture shows you the landing platform together with the rover. And finally, on June 11, 2019, we succeeded. This picture shows you the rover landed on the far side of the moon. Okay, this is the first example. The second example I'm going to talk about is the TW1 mission to Mars. This is the first China's mission to the Mars. As I just mentioned that, we tried to integrate orbiting, landing, and cruising together in a single mission. This is very challenging. In China, we use Tianwen to name all the exploration programs to the Mars. Tianwen is the name of ancient poem or poetry written by Yuan. This poetry is to explore the universal laws or rules. Of course, that was about 2,000 years ago. A lot of things were imaginary. However, today, a lot of things have been realized. Okay, anyway, TW means the name of Mars project in China. TW1 is the first mission. As you know, Mars is much more far compared with the moon. We use the AU to represent the distance between the sun and the Earth, and the distance between Mars and the Earth and beyond 1 AU. So, among the history of humankind to explore in deep space, the success ratio is very low. And here I can give you some figures. And if you look at the overall missions, the success ratio is 22/42, so about 50%. If you look at the successful landing, only 7 times were successful compared with 18 times missions. By the way, all the successful landings were completed by NASA based upon a lot of previous detections, including Mars information, Mars atmosphere, Mars gravity, etc. Based upon these informations, then you can design your orbiter, your landing system, and your rover. However, for China, we did not have enough information, so you can imagine that it's very hard for us to design the whole mission integrated with so many tasks. The right picture shows you the whole mission of TW1, and the probe was launched from the Earth and spent about more than 200 days from the Earth orbit to Mars orbit. Then it spends 93 days to observe Mars in detail, to select the proper location for landing, and to detect, for example, the density of Mars atmosphere, then to determine a lot of landing parameters. Okay. In this mission, the most tough problem is also related to mechanics, in particular dynamics. It's called EDL. That's the abbreviation of entry, descent, and landing. The question is that how to drop off your capsule at Mach 8, very high speed. Then how to utilize the Mars atmosphere to open your parachute at about Mach 2. It's very high speed. And how to reduce the landing platform from, say, Mach 2 to a very lower speed, for example, 3.6 meters per second. We use 4 steps to complete this EDL process. At first, we spent about 300 seconds to use the aerodynamics to reduce the speed. And then we open the parachute, use 90 seconds to reduce the speed further. Sorry. Okay. Then we start the engine to produce the compulsion, and then finally landing on the moon. To understand the EDL process, let me show you the detailed structure of the landing system. The landing probe is mounted on the orbiter, and then the orbiter will drop off the landing platform and then includes the capsule against the high temperature. Within the temperature, we have the rover for our detection and the platform together. And last, we have the bottom cover to conceal, to compact all these things into the capsule. Now let me show you some videos to demonstrate the whole process. The first step is to drop off your capsule or the landing probe. And then after it enters into the atmosphere, you can see the effect of the interaction between the capsule and the rarefied gas. This is the first step. Then we open the parachute at about Mach 2 and then drop off the bottom cover. Let the speed goes down rapidly. And then in the third step, when the probe was at a height of about 100 meters, then we open the laser detector to monitor the 3D surface or the Mars surface, then to select the best location point. It will have maneuver and moving horizontally. Of course, not very large, about 200 meters in circle. And finally, when the probe gets the proper information of landing, then it will open the landing engine again and finally landed on the moon. Okay, what is the mechanics? And here I'm going to give you 2 examples, use 2 slides to demonstrate the importance of mechanics. The first thing is that how to design the capsule. And we can get some information of previous Mars exploration. And however, actually, the shapes or configurations are not satisfied. Then we made a lot of CFD computation. For example, for rarefied gas dynamics, over 30 kilometers of the moon's surface, we need to use direct Monte Carlo simulation for the transition flow, and then use Navier-Stokes solver for the continuous flow. And we found that the previous shape or configuration of the capsule were not good enough. We cannot reduce the speed properly. So Chinese engineers decided to use 2 wings to reduce the speed and to increase the volume of the capsule and increase your controllability. So after a lot of iterations of optimal design, the final capsule configuration looks like the green one in the foremost right. Okay, this is the solid mechanics together with fluid mechanics. Then I will talk about the other problem, parachute dynamics. Since the moon has atmosphere, it's quite natural for us to utilize the atmosphere to reduce the speed of the probe by means of the parachute. However, we have never experienced to open a parachute at Mach 2, also at very lower density of gas, because the density of Mars atmosphere is about only 1% compared with the Earth atmosphere. So, of course, we did a lot of numerical simulations, and we found that the dynamic pressure is really very low, only say around 350 par, compared with a similar process on the Moon. Here is example of numerical simulation, and you can see the two shock waves. The top one is near the parachute, and the bottom one is near your probe. Of course, no people believe the result because it's just a try. So we need to do some ground tests to verify the correctness and efficacy of numerical simulation. So finally, we did 6 ground tests, very expensive one, including, say, the opening of the parachute in the left picture, including we launch the parachute to very high sky and at different speed, approximate to the real case in the Mars mission. And finally, we confirm that the numerical simulation is okay. Then we can complete our Mars mission. Okay, so we are lucky that about 2 years ago, on May 15th, 2021, the first Mars mission of China was fully successful. And later on, the rover moved about 2 kilometers away on the Mars surface within the first year. And then the platform and the rover together sent a lot of data, about 1.1 terabytes data to the Earth. And the right picture shows you the trajectory, the path of the rover on the Mars. Okay, this is the end of my second part. Now let me say a few words, or let me say more or in detail, talking about my research related to those missions, in particular, the demands for large space structures. Nowadays, we have increasing demand for the size of space structures. As you know, the solar panels are a mature technology, and or called conventional space structures, large space structures. The size of a solar panel can be, say, 10 meters or even 20 meters in diameter or in length. The deployable structure that I'm talking about today refer to the space telescope and space antennas, because they do not only have large size, but also very accurate configuration. That's very tough work. Of course, nowadays, people are interested in even large space structures. We have some basic concept design about the solar power station. It will have a size over 1 kilometers and even to 10 kilometers. Here, I show you some examples. Regarding to the space telescope, this is the well-known James Webb, has a size 6.5 meters in diameter. So compared with telescope, you can see those persons are so small. So 6.5 meters is a very large size. However, these are not satisfied. And the right video shows you the deployment process of Harris antenna. It is 16 meters in diameter. This kind of antenna can be used for telecommunication and Earth observing, and also space observing. So regarding to the solar power station, this picture shows you the length is 7 kilometers and the width is 1 kilometers. So how to get or construct those large space structures? this is a very challenge for space engineers. And because we need to deal with those problems. The first is the reliable deployment. The deployment is very complicated. And for example, the former Soviet Union and the United States failed times to times, even for the deployment of a space structure less than 10 meters in size. And this video shows you the ground test at my lab in BIT. You can see that the deployment process on ground looks quite complicated, especially for the very soft mesh reflector. This structure is the hoop truss supporting very soft mesh reflector. We need to confirm there is no entanglement of those mesh, because in the ground test, the mesh always falling down. However, in orbit, no people knows it goes, say, upward or downward or leftward or rightward. So we need to confirm the computer simulation be actually accurate enough for your mission in sky. So if you talk about the configuration accuracy, it's a more challenging problem, because just as I mentioned in previous example, for the moon's exploration, we sent a relay satellite with the antenna of about 4 meters in diameter. And I show you that the diameter divided by the mean square arrows of your reflector is a very large number. The larger, the more difficult. However, for these antennas, usually this ratio will be beyond 10,000, even difficult than the relay satellite in the lunar mission. For example, the right picture shows you an Earth observing satellite made in China for launched about 10 years ago. To guarantee the accuracy of the antenna configuration, at that time, Chinese engineers used relatively rigid panel reflector in yellow range bottom. So, however, if you are going to use the mesh reflector, it's very tough work for you to keep proper configuration and a very exact shape. In particular, when your satellite goes into the illumination region and goes out from the shadow of the sunlight, we will have the thermal deformation and thermal vibration. Now let me talk about some techniques a little bit in detail. And you have seen the deployment process of those large space structures. It includes the overall motion together with the elastic deformation. So we need to deal with this problem. Specific term should be flexible multi-body system, an important field in dynamics. Basically speaking, we have two kinds of approach to describe the overall motion and large deformation together. One basic idea is to establish a floating frame of reference for your moving body. You simply fix your frame on the moving body here, for example, A point A. Then this way, it's easier for you to describe the moving of the material point P. It's certainly the summation or two position vectors. Vector A means the overall motion of your body frame, and AU means the deformation of point B compared with the floating frame or body frame. Then we have the result in the middle of the picture. If your deformation is very small, then you can use so-called modal coordinates to replace the physical coordinates. This way you can greatly reduce the dimension of your system. However, only in the case when the deformation is small. In addition, your rotation speed could not be very large. Of course, recently, a lot of people tried the new approach based upon more advanced mathematics, such as the Lie group SO3 or Lie group SE3. And this way, we need to establish the local body frame at each nodal point of your finite element model. Okay, that's a complicated story. I'm not going to continue. The second approach is to give up the body frame. For example, we simply use fixed frame here, can also called absolute frame. Based upon this frame, we can simply interpolate the dynamic configuration of point P according to the four, for example, nodal points information 1, 2, 3, 4, 5. 1, 2, 3, 4. However, we need to use both position vector and slope information of the vector. This kind of approach was first proposed by Professor Shabana in University of Illinois at Chicago. And nowadays, the approach is called ANCF. Compared with the advantages and shortcomings of these two approaches, ANCF is quite universal. However, the elastic forces and internal forces have very complex formulation. Before the study of my team, this kind of approach could not be used for real engineering problems. So what we did over the past 10 years to develop this idea to be more realistic, to deal with more real problems in engineering. For example, we proposed new finite elements based upon the idea of ANCF. They are superior than other finite elements in commercial software because commercial software cannot deal with the deployment dynamics of space structures. Here are some comparisons of our result and those offered by commercial software. The right picture shows you the large deformation of various beams have different cross sections such as I section and rectangular section or hollow rectangular section. And the left picture shows you the comparison of element with commercial results. And commercial software can only predict a twist like this way, about a half circle. However, the elements we developed can predict a very large twist, about 10 circles. This is very important for the soft deployable structures in space engineering. Here are some other examples of finite elements. You can see the very large twist of those beams. And we also have, say, the shell elements to predict very large deformation and even including plastic formation. And the membrane element to simulate the spinning rotation, spinning deployment of solar panels. And we also have the solid elements to predict the overall motion and large deformation of those structures. In addition to those elements, we based upon the so-called arbitrary Lagrange Euler description to establish new element to describe the beams with a variable length. In the right videos, you can see that the length of the beam is increasing during the spinning process. Okay. After we have those new elements, we can only predict some simple deployment process without any context of your components. So we need to solve the problem of context between two soft bodies. First of all, let me talk about the contact between two terms. It looks very simple. However, the computation actually is very complicated because we need to compute the distance between two beams to identify whether they get contact, get in touch together. And then if they both get in touch, we need to determine the contact region in shadow in the middle picture. And then we need to compute the normal contact force and the tangential contact force. The tangential contact force depends on the friction. That's also very tough problem in mechanical engineering. And we are lucky that the right video shows you agreement of a numerical result and the experimental result. And the time history looks very good agreement. Okay, of course, the more tough problem is not the contact between two beams. That's the contact between two soft surfaces or soft bodies. And this way, we cannot get exact solution. Usually, we prefer to have so-called weak solution in integral form like this. And here, the vector lambda lies on the friction core, and the vector g lies on the complementary friction core. And then I give you the examples of the contacts between two soft bodies. This is the contact of two half-cylinder shells, and the bottom figure shows you how a soft gripper can grasp a torus-shaped figure object and move it and then release it. Okay, based upon those techniques, then we can predict the deployment dynamics of a complicated, for example, satellite antenna reflector. And this video shows you the process of a satellite, communication satellite. First, you deploy the two solar panels, then the deployment of the microwave signal feed source, and then a very large antenna. Of course, these truss is supporting the soft mesh, so I give you the comparison or in the left videos. The top video is the numerical simulation, and the bottom video is the ground test at my lab in BIT. This is the most important stage because we need to identify whether we have any entanglement of the mesh. So here are the comparison of numerical results and experimental results. And from this figure, you can see that deployment angles get very good agreement. We can even predict some stick-slip phenomena within the joint of the truss. Okay, actually, this kind of approach is quite universal for not only, say, the deployment of space structures, but also for many other techniques. Here, I give you the second example of flying net, which can capture a disabled satellite or the space debris. This is the test rig developed at my lab in BIT, and the right video shows you, okay, I don't know why. Actually, the top video and bottom video should start at the same time, and then you can see that the flying net goes upward and the same configuration we observed in experiment. Maybe different computers gives you different result. It doesn't matter. Anyway, they are very useful approach for many other applications. Okay, this is the last part of my lecture. I'm going to talk about autonomous assembly of space structures, because with an increase of space size, and later on we find that it's not possible for us to deploy everything in orbit, because if your space structures is very large, even though you compact it into a small volume, you cannot put it into your carrier rocket, especially in China. The diameter of most of the carrier rocket should be less than 5 meters. So, for example, if you are going to construct a large satellite over 100 meters in diameter, it's not possible for us to put this single antenna into the rocket. So this way, it's quite natural for us to construct large space structures one by one module. So this way, we need to design an ultra large space structures and based upon the modularization. What I mean that, for example, your antenna should be designed like this, either in the concept of NASA or in China. Usually we use the hexagon module, a lot of hexagon modules to compose a single large space structure. And of course, this way we need to solve a lot of new problems. In particular, all those kind of ultra-large space structures should be constructed by robots rather than astronauts. So basically, we are developing two kinds of approaches. One approach is based upon moving robots, and the other approach is based upon flying robots. Let me talk these approach. Regarding to the moving robots, the basic way to construct a large space structure is certainly how to design those hexagon modules and how to assemble them together. It's quite easy for you to understand that if your module is designed in the same size, due to the manufacturing error, you cannot fix or put into the last module during your assembly. Yeah, that's a very easy thinking. So it's better for us to let our module size be adaptive to the change. So for example, due to the sunlight, due to the thermal environment, etc. Okay, by the way, your robot must move on a very flexible structure because during your construction, your robot needs to move on the flat structure step by step. And this way, it's quite difficult for us to control a robot moving on standing on a moving basement. Okay, I'm going to talk about some initial studies in this field. The right picture shows you the assemble sequence at my lab in IUAA. You can see, say, this is the first module, and then second module, 3 modules, 4 modules, and finally 7 modules. And during the test, we found that it's really difficult for us to insert the last module due to the manufacturing errors. So now we are going to design some adaptive modules to solve the problems. These two videos shows you how the robot senses an object automatically and then grasps it and then fix it somewhere. I just mentioned the robot is working on a floating frame, the moving base. So according to the conservation of your momentum, then when, for example, your arms move toward the right, then your basement will move in opposite direction. That's a problem. This is the ongoing research of my team. Regarding to the flying robot, actually, this approach is more flexible. It can deal with even more complicated case. However, it also has some shortcomings, including, for example, the consumption of fuel. Of course, it has more risks. Here are some basic ideas of JPL and my lab. And the right figure shows you that, for example, your very expensive antenna is damaged due to a small piece of space debris. And then our service spacecraft can fly, orbit your satellite, and then get rendezvous and dock to detach a small module, and then replace it with a new one. And this is the final purpose of my research. And now we are doing some fundamental studies towards this objective. Of course, we need to design the flying robots with the ability of, say, avoidance of obstacle and rendezvous and then dock in a very cheap way, rather than the whole process like, say, the China Space Station. That's very, very expensive. Okay, you can see one satellite moves and avoid any contact with the rest satellite, and then rendezvous to the third satellite. The third satellite is spinning, so they need to have the same spinning rotation and then get closer and closer, and finally the two red dogs get together and completed the docking process. No matter whether you're flying robot, smart, or you use even a lot of new technology of artificial intelligence, it's still the most dangerous process for your final docking, because both spacecraft are flying at very high speed, about 8 kilometers per second. You need to control the relative distance and the relative velocity to a very slower range, very lower range, for example, 0.1 meter per second. That's too difficult. So the better way for us is to design some new gripper to adapt to the variation of your relative velocity. And here, my team member designed a bistable gripper. This picture shows you the configuration. It's actually at the bottom side, you can see the two soft beams crossed together. And actually, this is the one stable equilibrium position. If the bottom top of the gripper touches anything, it will suddenly change the shape to the other stable configuration, and the cross will grasp the object firmly. Let me show you the video. Yeah, the video does not start from the very beginning. Actually, the yellow block, a cube satellite, moves toward the right side and then hit the gripper all of a sudden. Then the gripper changes the configuration and then firmly grasps it, complete the docking process. The video does not work. Anyhow, most of the ground tests nowadays are based upon the two-dimensional ground test supported by, say, the air suspension. However, the real assembly process should be completed in three-dimensional space. So we also pay much attention to simulate the three-dimensional space with a microgravity. The right picture shows you the ongoing work of my team. Okay, now let me say a few words to conclude my lecture. First of all, the past 70 years have witnessed the success of China's space engineering, proposed and initiated by Professor Chen Xuesun and developed by several generations of young talents. Of course, the influence of Professor von Karman is very important during this process. The second is that the large deployable structures have well served China's space missions, but nowadays we need even larger space structures, or called ultra-large space structures. And this kind of structure is still in ongoing research. And finally, nonlinear dynamics and control play an essential role or important role in advanced techniques of all kinds of large structures. So I hope young people will be involved into this process. Thank you so much for your attention.
Professor Hu, we were all most impressed. I was especially impressed by the scale of the structure you dealt with, and also by the amount of smartness you built into them. But then just thinking a bit further on, so the space is infinitely large. China is a giant country with a giant nation. So to me, to do research in the space by China, so space and China go very well together. I think it's even a must for your nation to deal with that for the achievements of the mankind. Let me, however, mention that we, Hungary, small country, small nation, but very powerful, we also deal with space research, space engineering. It was a couple of days ago we launched the very, very small satellite. So this is the other end of the scale. So you deal with very large scale, and we deal with the miniature ones. And I guess one day we will meet in the middle somewhere, and it's more than useful to cooperate. And I just hope that the cooperation you conduct with Hungarian researchers will continue, and this event will just strengthen all that. But let me then add some quotes relevant to your lecture. So there are, of course, several quotes from Albert Einstein. One says, "There comes a point in your life when you need to stop reading other people's books and write your own." As far as I understood, this point came to your life at the age of 42. Second, let's continue with Konstantin Tsiolkovsky.
42 at age 42? What? Sorry, I beg your pardon. Could you please repeat the first question?
So we know your biography better than you do, I guess. 42 is too much of a young age to you, writing your first book.
Oh, first book.
Right.
42, okay. 42 years younger. Anyhow, yeah, please continue.
What is for sure that you are 1 year older than I am.
Really? Okay.
Right. So let's move on to Konstantin Tsiolkovsky, whom we all know, who died in 1935. He wrote once, "To set foot on the soil of the asteroids, to lift by hand a rock from the moon, to observe Mars from a distance of several tens of kilometers, to land on its satellite or even on its surface, what can be more fantastic? From the moment of using rocket devices, a new great era will begin in astronomy." I guess you are a player in this very new era. And we believe that your lifelong research work definitely contributed to achieving these visionary views mentioned by Professor Tsiolkovsky. At last, the little-known quotation of Theodor von Karman says that some fear flutter because they do not understand it, and some fear it because they do. So we believe that you, Professor Haiyan, who proved that you understand Flutter and still does not fear Flutter because you control it, such as. Anyway, thank you for this inaugural lecture. That was wonderful. With this, Professor Haiyan, who fulfilled the last one of the criteria for receiving the sealed document signed by the President of the Hungarian Academy of Sciences about his honorable membership of the Hungarian Academy of Sciences. So it's my special honor to to present the diploma, proving that to you, and to be the first to congratulate to you. Thank you very much.
Thank you so much.
So that's it.